How electrons make light.
In this video, we're going to put a lot of things together. We're going to review ground state and excited state and what that means for atoms. We're going to go through the steps that atoms go through when they produce light using a simulation.
Atoms start in the ground state, atoms absorb energy and move to higher energy levels. This is the excited state. Atoms emit or release light energy and move back to ground state.
And we're going to connect it all back to the emission spectrum. So get out a piece of paper to take some notes, and also you'll be answering some questions as we go. Let's get started.
A light bulb is filled with hydrogen. Turn it on and it glows. Why? Even more interesting, this is the emission spectrum we see when we use diffraction glasses. Where do those lines come from? To find out, let's use this simulation. Here's a hydrogen atom. You see the positive nucleus and one electron there. And up above, you see
part of the electromagnetic spectrum, and right in the middle is the visible light spectrum. And on this side, we see shorter wavelengths, higher energy, that is invisible. And on the other side, we see the longer wavelengths and lower energy. But both sides of that, the higher and the lower sides, are invisible, and just those colors in the middle are visible. They are all waves, and they all carry energy.
Let's look again at this zoomed in picture of a Bohr model of hydrogen.
Hydrogen has one electron. You see that in blue. Right now, the one electron is in the first energy level. The energy levels are areas the electrons are flying around in. We number them 1, 2, 3, 4, 5, 6, 7. So it's in the lowest energy level. We call this is a new term, the ground state. A state of being. So right now the electron is in the ground state. It's closest to the nucleus in the lowest energy level, just like if you were standing on the ground and being very calm. But what you're going to see in a second is that electrons sometimes will move out of the ground state. And when they do, they go up, they jump up into higher energy levels. And we call that the excited state. And that'd be kind of like when you're jumping up and down, little kids all excited, jumping at a party. So watch as I show you with the simulation, the electron moved from the ground state up into the excited state.
To the ground state again.
Okay, so this represents a hydrogen atom with its one electron in the first energy level.
The ground state.
You can kind of just see part of the atom here, right? Because we're zoomed in really close. But let's see what happens if we add energy. In order for the electron to move into higher energy levels, it needs to absorb energy from some outside source. That might be from
electricity, like with the light bulb, or
heat from a flame. It might be light from somewhere else coming and hitting it. So if it absorbs a certain amount of energy,
the electron will jump into higher energy levels. The amount of energy needed to jump from level 1 to level 2 is represented by a wavelength of 121.5 nanometers or 985 kilojoules per mole of energy. Let's look at that again. Usually atoms are in the ground state. We can't tell if a gas is coming from the stove, because if it is, the atoms are in the ground state. But when I use a match, the heat energy is transferred to the atoms of the gas.
Now, if atoms absorb enough energy, the electrons will fly around and actually get enough energy to jump into higher energy levels. Like here you see it absorbed 121.5 nanometers, and you see the arrow up above, that's in the part that's higher energy than what we can see.
The electron is now in the excited state in the second energy level. But without a constant input of energy, the electron will fall back to the ground state and emit or release energy.
It releases the exact same amount of energy. So this is representing an invisible wave of energy there.
What if the electron gets enough energy to jump up
here, and then it gets even more energy and can jump up to here? Now you see it's absorbing a wavelength of 656.3 nanometers, and that is in the range we can see. That's going to look like a red light, but when it's absorbed by the atom takes that energy in. So now the electron is in the third energy level. It's higher than it should be, right? This is not how we usually draw atoms. We were drawing them in what we call the ground state. And now it's in the excited state.
If this electron emits energy or releases energy,
it releases, again, the exact same amount of energy that it had just absorbed. And that is what we would see as a red light being released from this atom.
like we see on this emission spectrum of hydrogen.
Let's see if it were to jump up 2 energy levels, how much energy would have to be absorbed for it to jump up that high. It's absorbing and absorbing more. It absorbed 486 nanometers, and you see that that is from the blue part of the spectrum. And when it falls, what do you predict? If it falls back to that same level, back to level 2 where it had been before, so 2 levels, what will it release? It releases that blue light again. So it absorbed the wavelength 486 and it releases that wavelength when it comes back down.
So this would make a blue line on the emission spectrum. As you are seeing,
these are specific colors that hydrogen will
produce when it absorbs and releases energy.
Let's see if it goes from that second energy level up. 1, 2, 3. Now it absorbed 434 nanometers wavelength. And we see that is kind of on the edge of the visible part of the spectrum. And if it jumped all the way up there, now it's even more in the excited state. And if it falls back down, if it fell back down 1 level, it would release an invisible wave that's much longer than the visible spectrum. 2 levels, again, a little bit shorter wavelength, but still outside of the visible range. And 3 levels, there we see that purple one that it had absorbed.
And that's why we see a purple line on hydrogen's emission spectrum. Now, if it moves all the way to 5, that's absorbing a lot of energy. And if it releases that same amount of energy at 410 nanometers, that's right on the edge of the visible spectrum, almost to ultraviolet.
Now, if you're paying attention, you might be noticing this is not even in the ground state yet. It's still up in the second energy level. So when that electron finally falls all the way to the ground state, it will also release energy again. You'll see a wave coming from it. But remember, that's that invisible high energy wave.
Okay, back to the hydrogen light bulb. Why does it make this light? So when the electricity is turned on, the electrons on the atoms of hydrogen get excited, absorb energy, and jump up to higher and higher energy levels. And when they return to the ground state, they release that energy in the form of colored light. And they always release the exact wavelengths that you see here in this emission spectrum, which is the unique fingerprint of hydrogen.